The most important truth about underwater breathing is that it is not really about oxygen. It is about carbon dioxide, heat loss, and human error, all piling up fast. As of 2026, open-circuit scuba still dominates civilian diving for a reason. It is mechanically simple. You can inspect it. You can train it at scale. The big penalty is efficiency. Every exhale dumps usable gas into the water, so endurance is limited by what you can carry. Rebreathers exist to change that trade. Semi-closed and closed-circuit systems recycle most of what you breathe. They stretch time underwater, reduce gas logistics, and can run with an optimized breathing mix. They also reduce bubbles, which matters for wildlife work, science surveys, industrial tasks, and tactical missions. But the price is procedural burden. You are now running a compact, life support plant on your back, and the plant can fail. That leads to the first high-impact constraint: oxygen partial pressure control. Too little oxygen and you risk hypoxia with little warning. Too much oxygen and you approach toxicity limits, especially under depth. In a closed loop, oxygen is not a static tank value. It is a continuously managed variable, and it demands sensing you can trust, control that behaves predictably, and alarms that a stressed diver can actually understand. The second constraint is carbon dioxide removal, and it is more treacherous than most outsiders assume. Rebreathers depend on scrubbers using soda-lime family mixtures and similar absorbents. Capacity is measurable, but it varies with age and condition. That is not a paperwork detail. It is a reliability variable. Real endurance depends on packing quality, canister design, breathing rate, temperature, humidity, depth, and workload. Change those inputs, and the same scrubber can behave very differently. The problem is not just scrubber exhaustion, it is knowing it is happening in time. Breakthrough the moment CO2 slips past the scrubber is a make-or-break safety function. Predicting it in real time is hard because every extra sensor or algorithm can also add new failure modes. Underwater life support is ruthless that way. Complexity can save you or it can kill you. A third constraint is breathing resistance, especially under depth, cold, heavy workload, or partial flooding. Extra work of breathing pushes physiology towards CO2 retention. Cold water adds another pressure, literally pulling heat out of the body. Thermal protection is not comfort, it is operating margin. If a diver gets cold, performance drops, dexterity fades, judgment narrows, and small mistakes multiply. All of this points to a counterintuitive, strategic conclusion. The limiting factor is often not the hardware, it is coordination. Maintenance discipline, training quality, checklist compliance, and incident learning determine whether advanced gear becomes an asset or a liability. That is why the same themes repeat across military units, scientific diving programs, offshore work, and first responders. Each needs auditable procedures, credible qualification pathways, and a culture that treats the equipment like aviation, not like a hobby. A useful lens here is mission-level coupling. Underwater work is rarely just a person and a device. It is a system. Surface teams, standby rescue, communications, medical response, spares, transport, decompression support, and recovery planning shape what endurance really means. If procurement only buys the wearable unit and ignores the support architecture, the organization is buying risk. Now consider what progress looks like in the near term. From 2026 to 2050. It is not magic breathing media. It is better sensors, stricter logging, more fault-tolerant alarm logic, and digital checklists that actually get used. It is also governance around consumables, including storage conditions, age controls, rotation, and post-mission accounting. Rebreathers can become safer without changing the basic physics if the support layer becomes more rigorous. The key idea is simple. The device should be able to expose configuration, consumable age, calibration state, service history, and alarm events in a structured way, even across vendors. Achieving that is less about inventing new parts and more about standards, procurement language, and liability alignment. Biomedical monitoring may also join the stack, but it has to earn its place. Signals underwater are noisy, and false alarms train people to ignore warnings. But if you can reliably detect rising CO2 retention risk, thermal stress, panic, or impairment early, you can shift from post-incident review to real-time prevention. Finally, a hard boundary: liquid breathing. It remains a boundary concept here, not a fielded personal life support system. No verified milestone demonstrates practical, untethered human underwater liquid breathing in real operations. Claims should be treated as speculative unless a verified deployment pathway emerges with credible solutions for ventilation, CO2 removal, airway management, and emergency reversibility.